So let's try again. My name is Adenilson Cavalcante. I work for Intel. I'm based here in the San Francisco Bay Area. Together we have Gustavo. Gustavo, are you there?
Yeah, hello everyone. Thanks for having me. I work at Intel as well with Adenilson.
Okay, and today we have Znews, news from Chromium zlib. Right, notices and disclaimers. All right, why should we care about zlib? Up to these days, most of the compressed content in the web is still served using gzip, even though alternatives like Brutally are growing. And to give a little bit of context, Chromium zlib is a fork of canonical zlib. It's heavily patched on top of canonical zlib, has many optimizations, low-level optimizations targeting both x86 and ARM architectures. And in average, should be almost 3 times faster for data decompression. And today, around 60% faster for compression. It's been in active development since 2017, and is used everywhere by Chromium, Android, Node.js, V8, and since last year by Google Fleet. So what are the objectives? The objectives are to share current status and share some of the new ongoing optimization research. Right, let's talk about security maintenance first, because security matters. We have completed in last May the sync with zlib 1.2.13.1 that featured 2 important bug fixes, one for deflate bound and another fix for crash on GZ set params. On top of that, Mark Adler, who is the maintainer of canonical zlib, he updated the whole code base to use modern C style. For people who are not aware, until last year, zlib was still using Kernighan-rich C style. And I would like to say thanks to Chris Bloom and Hans Weinborg for reviewing lots and lots of patches. On top of those fixes, there are 2 important fixes. The first 2 fixes are related to minizip, which is an auxiliary library built on top of zlib that is used as an example for opening zip files on Chrome OS. Those fixes they were implemented by Hans, and they were later ported to canonical zlib. And also another fix provided by Philip Parrish related to the internal window location used for data decompression. Nice, but you guys came here to talk and see about performance optimization. So let's discuss first decompression. Right. Last year, Douglas Johnson has published some brilliant research concerning optimizing zlib. I highly suggest everyone to have a look on his web blog. I have the links here on my slides. So let's start by talking on the first optimization. The idea here is that zlib uses LAMP07 and Huffman coding. And by leveraging a flatter Huffman table, we can have a bigger root table, and that helps to avoid some branch mispredictions in lookups for the Huffman codes. That comes with a price of, say, 1.9 kilobytes per inflate state, but the average gains, they were really impressive. They ranged from 5% in average for Haswell, and up to 8.3% on Cortex X1, and landed September last year. The second optimization was unconditional refill of literals. The basic idea is that on the fast path, while we are performing data decompression, we decode up to 2 literals if they are present on the root table. That, of course, generated some change on the requirements of inflate fast chunk. But the improvement was really, really interesting. As an example, the average gains for Ice Lake were 16% and almost 12% for Sapphire Rapids, but that is the average. In some contents like HTML, the gain was a massive 46% faster data decompression, and we ended February this year. And if people are curious, we have a link here with a spreadsheet with all the data. It's possible to see that, say, on Apple Silicon, the average gain was less expressive than, say, on those Xeon processors. The third page was a contribution from GLU and Lei He. They are teammates from Intel in China. The basic idea was to port the SSC 4.2 code we had since, I believe, 2018 to use AVX 512. People who never worked with AVX 512, I would say it's relatively easy to port, say, code from AVX 2 or SSC 4 to AVX 512. And the hash speed improved in 3.5 times. But the average gain on data decompression was less expressive, was just 3.7. Basically because when you have, say, a pipeline, and you already have a really fast hashing, by making that even faster, the overall gain is not going to be huge because we are bound by Amdahl's law, right? But it's still quite interesting. It landed in April. And also, I think it's interesting to mention, last year I landed a PMO Cindy implementation for CRC32, but that was enabled only for Apple Silicon. What was missing was CPU features detection code for iOS. Dave Tapuska from Google, he submitted a patch to us. And it was really nice because the average gain was a 17% faster compression in average and 10.5% faster decompression. It landed last July. So this is a chart showing what were the gains for all those patches running on Sapphire Rapids. The average gain was 28% faster data decompression. If, say, you assume that between a new generation of silicon, you expect something between 10 to 15% faster processing, 28% will be about 2 generations of silicon. Of course, in some data files like HTML, the gain was over 50%. In other data files like, say, JPEG was a small regression. But generally speaking, those patches, they behaved pretty well together. Okay, now let's talk a little bit about data compression. Even though in a web browser, generally we don't do compression as much as, say, decompression, given that the fleet has adopted Chromium zlib last year, I start to pay more attention towards optimizing compression. And I'm going to try to share 4 decades of history in less than 5 minutes. All right, so looking at the art of computer programming by Donald Knuth, there are 2 requirements for a good hash. The first is that it must be really fast. And second, it should minimize collisions. And Donald Knuth proposed in 1973 division hash. But back then, the module's operation used to be quite expensive. And it was implemented in zlib in early 90s. And this is how the hash looks like. So as a matter of fact, they are using a shift followed by an XOR as a trick, instead of, say, doing a division in a module. And I was curious because I looked at the code and I was like, all right, what is the origin of this source code? And doing some archaeology, I discovered that in 1985, there is this Unix compress application, and they implemented a division hash variant using XOR. that would be like a good speed up. And this is how the source code on Compass 5.0 looks today. This very cool. They even mention like the Donald Knuth book over here. And you can actually compare Compass hash versus zlib hash. And you can see that it's pretty safe to assume that is the origin of the hash used in zlib. Right. But until like last month, Chromium zlib was using CRC32 instruction as a hashing instead of, say, the division hash that was first introduced for Intel in 2015 and for ARM in 2018. Specifically, should yield an average between 20 to 30% faster data compression than using a division hash. And it's really fast. I mean, the instruction takes like 3 cycles on x86. On ARM, it can take between 2 to 3 cycles. But Donald Knuth also describes the multiplicative hash as a better option. And Hans Weinborg suggests that we should have a look on a Bertolli's hash, that is the multiplicative hash. And Noel Gordon, he shared a pretty interesting hash he called ANZAC++. And these are the results of leveraging this faster hash. Basically, for Sapphire Rapids, the performance gain was almost 42% faster data compression. On Ampere was 34%, Apple Silicon 31.6%. And if, say, you are interested, you can have a look on the link where there is like a spreadsheet with the whole data. And this is what is the breakdown for different inputs with different entropy properties. So in some cases, say HTML, compression became like around 25% faster. In other cases, say some text files, the boost was like 80%. So it's almost like twice as fast. And even for data inputs with really high entropy, those files are called bad data. This is the snappy data corpus. The gains were pretty good, I would say. So the key points here is that by using a multiplicative hash, we improve the data compression speed between 31% to 42%, depending on the CPU architecture. The compression ratio loss was minimal, was less than 0.1%, because this is the key. I mean, we can make things faster, but maintaining the same compression ratio can be really challenging. And remarks that the zlib hash, even though it's like a division hash, is also a Rabin cart rolling hash. And there's a difference between, say, hashing 4 bytes when we use CRC32 or when we use a multiplicative hash versus hashing 3 bytes, which was the original implementation. Which also means that the match length, the minimal match length for, say, length set 7 is going to be about 4 instead of 3, which may explain why we lose a little bit on compression ratio. But 42% improvement is like 3 generations of silicon. That is thanks to software optimization. So if there is like a lesson here is that even a highly optimized code base, there might still have some good opportunities for improving the performance. Now I will pass the presentation to Gustavo. Gustavo?
Hey everyone, I'm Gustavo. Yeah, so I'll give you a quick overview of some work that we have been doing with QAT for accelerating compression. And a little bit about QAT, it's a hardware accelerator from Intel. It performs both compression and cryptography, but it usually was a separate PCI card. But from Sapphire Rapids and newer models, we have it in silicon, so it's a bandwidth benefit in there. Next slide, please. So a very high-level overview of how it works. You have at the very bottom the specific device driver. You have your QAT kernel module right now in 3 on the kernel. You also have a very special memory allocator that you need for physically contiguous pages to be mapped each to your process address space. And then on user space, you have QATLib, which is the official Intel library. QATCPP, which is a small project that we have been working on. It's a small C++ library that provides memory safety and also a simplification of QATLib. And you can have any application link into that. So now we're going to perform a quick demo here. So it's a small video we made. So you have cpipe on the top and a small program we made on the bottom. So the program on the bottom, you can see that it's finished already, but cpipe takes a lot, like 50 times or something. But the difference here is because pipetest is completely performing compression on hardware. And a fun thing to mention here is that pipetest is almost exactly the same as cpipe, but it's not actually using zlib, but instead it's using an interface that it's identical to zlib, but internally it's using QAT to accelerate compression operations. And you might think that this is the results for any file, but it's not. We have some data here for other files from the same corpus that Adi was mentioning before. And that's on the next slide. So our average performance boost here is at 30x, which is a huge number considering that it's performance related. And since the results are very varied, in like you have 70x on top, and some of the others are not so high, it might seem that like the bars are very low, but they are actually like 6 or 7x, which is still a huge improvement. But yeah, overall, we have not seen any performance decrease compared to CPU, and that's actually really cool. And well, that's all I have to tell you guys, and thank you for having me here in this conference.
All right, Gustavo, nicely done.
Yeah.
All right, so what are the next steps? We still have work to do using software. I think we can still improve the compression about 15% on top of what we have achieved already. Compression work still has some good potential, to say maybe 20% on top of what we are shipping today. Hardware, we are still under the beginnings, but I believe everyone here was able to see the huge potential that it has. I mean, 30x, I would say is fairly massive. And also patches are welcome. I'd like to say some special thanks to what I call the Z team. That is Hans Weinberg, Noel Gordon, and Chris Bloom. It's not like an official team or anything, it's just like a group of individuals that have an interest, a shared interest in data compression. I'd like to say thanks to my Intel teammates, Gustavo and Gia Liu. And also we should remember Jean-Luc Gale and Mark Adler, who are the creators of canonical zlib. Especially Mark Adler, he has been maintaining zlib for the last almost 30 years for free. And especially my family, my wife and my daughter, for being so understanding of my zlib obsession. And some last words by the founding father, Donald Knuth. Don't believe just because something is trendy that is good. I think you get more prestige doing good science than popular science. If you go with what you really think is important, then it's a higher chance that it really is important in the long run. And it's the long run that has the most benefit to the world. I started work on Chromium zlib almost 7 years ago. And it's really funny because every year I started by thinking, well, I mean, this is it. There's no freaking way we can make it even faster. It's really exciting that there's always like some new opportunities. There is always like some new collaborations, new contributions from other developers. And so far, it has been like a really amazing journey, I would say. All right, so I'm looking for questions. Feel free to ask questions.
All right, any questions? And anyone on the remote also can raise their hand. That one. Okay, 1 second. We got one from over here.
How much of this work is potentially applicable to Brotli or Z standard?
All right. I would say some ideas they could be reused for both. Direct code reuse, I'm not so sure. That being said, I would like to spend some quality time looking to broadly as a standard. Maybe when I call the job done on zlib, I will move to the next challenge. That would be really cool.
All right, we have a raised hand in the remotes.
Cool. Hi, Dunson. Great talk. So quick question about QAT and its capabilities. So how much of zlib, in theory, could be replaced by this hardware acceleration layer?
Okay, yeah, good question. Gustavo?
Yeah, currently we only have work for compression. Also, you might have to consider the fact that sometimes you cannot enable the hardware. There might be sometimes runtime errors or driver errors or something. So we always have this like fallback into software again. Currently, we're in very, very early beginnings for QAT in zlib, but the plan is to integrate that into zlib and have QAT perform all of the compression jobs and maybe in the future decompression as well. But yeah, you can actually completely use QAT on or make the hardware implementation completely without resorting to any software at some point.
Yeah, I think it's interesting to reinforce that right now, QAT is a server-only technology. It's only available on Xeon class processors, specifically Xeon 4th generation, Sapphire Rapids. That being said, you'll never know. I mean, what the future holds, right? Wink, wink.
I don't have the view of the room up right now. Do we have any other raised hands? Okay. Then I guess thank you, Adenilson.